Thanks, Tom. So what we're talking about is the one-loop correction to the photon, to the magnetic moment vertex, or the interaction of a photon with an electron. And we actually computed that result last time and got Schwinger's result, but in the computation I skipped a number of steps that actually Weinberg goes through in an earlier chapter.
To clarify,
And I think I'm going to do that.
I haven't looked at the website. Which volume of Weinberg are we in?
One, volume one.
Just the first one.
Yeah.
Can I ask something a little bit off this topic?
Sure.
The homework problem you put on there,
Yeah.
you say derive Feynman's trick. When you say
To the integral.
you just want to, okay,
It's a use.
so it's just solved.
It's two or three lines.
It's not hard. It's do the
No,
integral.
it's easy to do the
And I
integral.
made
That's the reason I thought
Yeah,
there was
so-
something wrong with it.
So did I.
I was like, okay, there's something wrong here. This
All right, I'll give you guys a harder problem.
That's okay.
No. I don't want Weinberg problems.
Okay, so let me just go through some of the things that we skipped, or that I skipped. One thing that I didn't skip was that P prime, S prime, the current JA of X, P has this matrix element we saw was e to the I P minus P prime dot X times the matrix element of the same current at the space-time point 0, and in particular current conservation, and that implies that that P prime minus P A, P prime S prime J A of 0, PS should be 0. So that's one thing that we worked through. And we also checked that the amplitude that we got, the integral we got from doing the Feynman calculation, the Feynman diagrams, was satisfies current conservation, and we were happy about that. Let me now say that the charge Q is the integral of J0 of X d cubed X, and because of current conservation, this charge is time independent in that partial Q partial T is an integral partial 0 J0 d cubed X, which by current conservation is minus an integral divergence of J d cubed X, which we turn into a surface integral of J dot ds at spatial infinity, and we just assume that this is 0. There's one case in which it actually is 0, namely if you're dealing with gravity in a closed universe, spatially closed universe, then the surface vanishes at infinity. But the theories, the ordinary theories that, well, extraordinary theories that might cause problems are ones with massless scalars, but they don't exist in the standard model. Now suppose we take the matrix element of the charge operator, and this is P prime S prime Q PS, and then this then is P prime S prime integral d cubed X J0 of X and T PS, and this then, of course, is, hold on, P prime S prime J0 of 0 PS times an integral e to the I P minus P prime dot X d cubed X. And of course this is a delta function of P minus P prime, in fact times 2 pi cubed. So this is 2 pi cubed delta cubed of P prime minus P times P prime S prime J0 0 PS. Sorry for the ugly writing, but it's hard to write well on a low board.
Is it P prime, delta cubed of P prime minus P, or P minus P prime? Sorry, I can't.
Well, it doesn't matter because
Yeah.
the delta function's even.
Yeah.
I wrote it as P prime minus P, but my notes have it as P minus P prime. So if you want, I'll change it just to make you feel better. But it doesn't matter because the delta function is even. It's the limit of something that looks like this. So it's even. On the other hand, we expect that the charge operator on the state PS of one electron is minus E times PS. And consequently, the P prime S prime Q PS is minus E P prime S prime PS, and this is equal to minus E delta cubed of P minus P prime delta S S prime. And this all goes to show then that the matrix element P prime S prime J0 of 0 PS is minus E, by the way, is positive in Weinberg's three volumes. It's the charge of the proton, not charge of the electron. So if you compare this expression here's the expression for the charge, and it's 2 pi cubed delta function, this matrix element. On the other hand, the same thing is minus E delta function delta SS prime. The difference is, comparing the two, we see that that's the matrix element of the current at 0. Now, I'm a little puzzled as to exactly what I covered last time. Let me cover all these, and I may duplicate something that I said last time, but repetition is the mother of studies. So, Lorentz invariance, oh wow. Lorentz invariance tells us that this U bar P prime S prime gamma A of P prime P, this is the thing we're computing. In other words, whatever this is to any order by Lorentz invariance, it has to be of this form. It has to be U bar P prime S prime and a gamma A times some function f of q squared minus I over 2m P plus P prime A G of Q squared, and then plus, I think I did this before, P minus P prime A over 2M H of Q squared. PS. Okay, well, the current is an emission, and so if you take the complex conjugate of this expression, of this matrix element, what you can show is that f of q squared is equal to f star of q squared. Same thing, G is G star, H is H star. So these three things are real. And now charge conservation, which is that P prime minus PA dotted into JA should give 0, means that if P minus PA is, P prime minus PA is dotted into this expression, we should get 0. That works fine for this term and this term. In particular, this term just gives you P squared minus P prime squared, so that's minus M squared minus M squared, and that's 0. This term gives you something proportional to P slash minus P prime slash minus P slash. On the other hand, the Dirac equations in momentum space are U bar of P prime S prime I P prime slash plus M equals 0, and I P slash plus M U of P and S equals 0. And one of the reasons, by the way, for this notation, U bar, and remember U bar is I U dagger gamma 0, and this is written as U dagger beta. So that's just the jargon of the trade. One of the reasons for this bar notation is that then the equation of momentum space looks like the equation for U bar, looks like the equation for U. If you don't have the gamma 0 there, there are funny signs that are confusing. On the other hand, this last term doesn't satisfy current conservation, because when you dot it in with P minus P prime, what you get is just Q squared, and Q squared isn't 0. So what you find is that H is 0. Okay, so at this point we're down to a simpler expression, which is U bar of P prime S prime gamma A of P prime P U of P and S is then U bar of P prime S prime gamma A F of Q squared minus I over 2M P plus P prime A G of Q squared U of P and S. In fact, since you guys complained that the homework was too easy, I think what I'll ask you to do is to show that these three guys are real, for by requiring you can assume that this matrix element is real. Now I'm hesitating because I'm wondering which part. All right, I'm going to have to think before I assign the homework. I'm going to have to
check to see exactly what is real here, because I didn't do this particular calculation recently. Okay, so this is our expression, and by Lorentz invariance reality, current conservation, F and G are called form factors. And if we now let P prime approach P, just to see what happens, what we get is PS prime JA of 0 PS. This expression here becomes minus IE over 2 pi cubed U bar of, okay, typo here. U bar of PS gamma A of PP, I guess, U of P and S, and this becomes minus IE over 2 pi cubed U bar prime, well, there's no prime, of P and S, so let me get rid of this prime also. PS prime gamma A F of 0 minus I over M PA G of 0 U of P and S. So let me just pause here a second to get
U bar of P and S or P and S prime?
where?
Next to, not the last equation, but up one.
Here?
On the U bar.
No, we're letting P prime go to P.
What about the S?
Oh, you're right.
How did you lose that power of 2 to the A?
All right, hold on, I gotta get this guy standing.
The Lorentz. When you let P go to P prime, you have P plus P prime raised upwards of A. How do you lose that 2? Am I not understanding?
Oh, there were 2 P's here.
Right, how did you lose
So
that?
P, if you said P prime equal to P, P plus P is 2P, that cancels the 2.
Right, but you don't need to worry that constant has that's a Lorentz index, right? That A is a Lorentz index.
Yeah.
You don't have to worry that there's a. I guess it doesn't. A doesn't affect the 2.
It's not a power.
I know, but it's just it won't matter either way. I guess that we can just suppress that or cancel it like that.
I don't see any problem here.
Okay.
What I think I skipped here somewhere, let me just see where it is. Okay, what I skipped at some point here was, so let me put it in here. Namely, that this matrix element that we've been looking at, Weinberg defines gamma A in terms of it. And so this is minus IE over 2 pi cubed U bar of P prime S prime gamma A of P prime P U of P and S. That's why we, from this expression, changing the gamma A and so forth to a J0, we get this expression. So it's just, in other words, we can exchange a gamma A for a JA at the price of an IE and a 2 pi cubed. These notes are online already. Okay, now, Dirac's gamma matrices, not only, well, Dirac's gamma matrices are defined by the rule gamma A, gamma B, anti-commutator is 2 eta AB. And of course, this anti-commutator is gamma A, gamma B plus gamma B, gamma A is 2 eta AB. And from that rule, you can show that the anti-commutator of gamma A with I P slash plus M which of course is the anti-commutator of gamma A with I PB gamma B plus M. This gamma A anti-commutator with gamma B gives you 2 eta AB. The eta AB just raises the B and makes it an A. Well, I did that in 2 steps. This is 2I PB gamma B. The M is just plus 2M gamma A. And so altogether this is 2I. What am I doing? This is an eta. Eta AB. This is 2I PA plus 2M gamma A. So this anti-commutator is that. On the other hand, Dirac spinors, did I write this down? Yes. Dirac spinors obey these equations. And consequently, between spinors of the same momentum, if we take the mean value of this, or the matrix element of this, between spinors with different spin but the same momentum. So we have here gamma A, I P slash plus M, anti-commutator, U of same P, different spin index. What we get is, in fact, we get 0. And the reason is that well, we get 0 because here since the P's are the same, when P slash hits this, I P slash gives you a minus M. When P slash hits from the other side, it also gives a minus M. And so we get 2 factors of minus M times a gamma A. On the other hand, M gives us 2 factors of M times gamma A. So we get 0. And we can and since the anti-commutator is this, we also have the result U bar of P and S prime 2I PA plus 2M gamma A U of P and S. That matrix element is also 0. And combining these two, we get another relation, which is U bar of PS prime gamma A U of P and S is minus I PA over M U bar of P S prime U of P and S. Now, there's probably a clever way of evaluating that inner product of spinors. But what I did was, I just used brute force, but the trouble is that the elegant way, I think, requires one to jump back and use the explicit Laurens expressions for these, which effectively is what I did. So you can write U of P of S as M minus I P slash over square root of 2 P0 plus M on U of 0 and S. So the spinors at finite momentum are given by the spinors of 0 momentum by this fraction times the spinors of 0 momentum. And so, by the way, let me just interject with a joke here that I heard way back when I was a graduate student. Somebody or other walked into T.D. Lee's office, Lee of Lee and Yang, at Columbia, and Lee was working out a detailed calculation on the blackboard or pencil and paper on his desk. And somebody asked him, "What are you doing?" And he said he was just doing exercises in gamma algebra to stay fresh. He was doing something like what I'm about to do. Okay, so let's compute what this inner product is. And as I say, there's a cuter way of doing this, but I'm just going to do it by brute force. So first I'm going to convert the U bar to I U dagger of 0 and S, gamma 0, S prime, sorry, and it's P prime. P, I'm sorry, gamma 0, U of P and S. On the other hand, now I'm going to use this expression twice, and I'm going to, well, I pulled out the I already. So this is I over, there'll be two factors of that, so this will be 2P0, P0 plus M, U dagger of 0 and S prime, M plus I, PA, gamma A dagger. So this is the adjoint of this. So the minus I goes to I, and the Dirac matrices get adjointed. And then we have gamma 0 and then M minus I P slash U of 0 and S. Now, the spatial gammas, gamma I dagger is equal to gamma I, gamma 0 dagger is equal to minus gamma 0. On the other hand, the gamma 0s anti-commute with the spatial gammas, and gamma 0 commutes with itself. The net result is that this is equal to I over 2P0, P0 plus M, U dagger of 0 and S prime, gamma 0, M minus I, PA, gamma A, M minus I, P slash, U of 0 and S. And so effectively this is now a little bit simpler. It's 1 over 2P0, P0 plus M, U bar of 0 S prime, M minus I, P slash, squared U of 0 and S. And so this is a lot of gamma algebra here. U0 of 0 S prime P slash U0 S is then, well, let me write it the way I did in my notes. I think it's a little clearer. This thing hasn't been cleaned in probably years. Where was I? Yeah, let's write this more explicitly as PA gamma A. So this earlier formula that we had, namely that the gamma A between two U's pulls out a PA and a minus I and so forth, that means that this is minus I PA and then delta A0 U bar 0 S prime U of 0 and S, and so this is equal to I P0 U bar of 0 S prime U of 0 and S. And then the standard anti-commutation relation, the anti-commutator gamma A with gamma B is 2A to AB. That lets us write P slash squared as PA PB gamma A gamma B, which this thing is symmetric in AB, and so this is 1/2 PA PB anti-commutator gamma A gamma B. So this is 1/2 PA PB A to AB, which is just 1/2 P squared, which is there was a 2 here though. This is a 2. So the 1/2 cancels. We just get P squared, which is minus M squared. And I see I've got a typo here. Okay, so this thing we can simplify, and when we simplify it, what we find is that U bar of PS prime, U of P and S is U bar 0 S prime U of 0 S over 2P0 P0 plus M. This structure then gives us 2M squared plus 2M P0. And so altogether this is just simply M over P0. U bar of 0 S prime U of 0 and S. And now we know what the U spinors are at 0 momentum. And in fact, U of, let us say, 1/2, or U spin up, is 1 over root 2, 1, 0, 1, 0. And U of minus 1/2 is 1 over root 2, 0, 1, 0, 1. And so when we take these inner products, we see we just get a delta, Kronecker delta. So this is M over P0 delta S S prime. Okay, so let me just get any questions while I get any more caffeine?
Do you mind explaining how you got that top row over here?
Okay, which top?
Not on the last board you're on the one right there, very top.
This,
up from there.
this one? Okay.
So
All right, let me flip back to see what I actually did. There's so much stuff on my notes here that I'm having trouble finding it actually. Here we are.
So without the PA in there, you would have a minus I PA over M, right?
It's actually a little. It seems to me that what I did here was. Okay, all right. It's what I'm using here is our earlier formula with U bar.
It's this one right here, isn't it?
Do you know where it is?
Right. Right. You're almost looking at it to your right a little bit, right there. Is
All
that
right,
what-
I'll write it down. This is the one I used. Oh yeah, it's exactly this. Right. So I'm using this. So I kept. Okay, what's confusing here is that this P has nothing to do with the spinors.
Okay.
The spinors are at 0. Over here, no matter what P is, the gamma pops out the P of the spinors. But on the other hand, if P is 0, the only part of the spinors that pops out is the time component. And the time component is M because the momentum is 0.
Okay.
So that pops out,
Okay,
this set
cancels.
A to 0 and pops out an M.
And it cancels that one. Okay.
And then if you keep the signs right, this is what you get.
Yeah, that makes more sense.
Yeah,
No, it's,
It makes
this
sense.
this is complicated.
Yes.
But as I said, there's probably reference to one of Weinberg's equations in chapter 5 would have simplified, certainly would have simplified this expression. I just did brute force. Okay, so now that we have this, let's look at what we've got. We've got PS prime, J0 of 0, PS, is equal to minus IE over 2 pi cubed. By the way, if you do look in chapter 10 of Weinberg, what you'll find is that he doesn't use Q. In fact, he uses Q for the charge of the particles because he does everything in general. But I'm talking about the electrons, so I said Q equal to minus E. Anyway, so what we have then, using the earlier formulas, what we have is you bar, well, there's no prime there. Of P and S prime, so these are the same P's, okay? We have minus I PA over M, F of 0, minus I over M, PA, G of 0, U of P and S. So that's going back to basically this expression written this way or that way, and then we've already set the momenta equal, okay, so I'm just recopying the same equation. But now, we've evaluated what PA is between these spinners, namely using this equation and this equation and so forth. So what we have is minus EPA over 2 pi cubed M U bar of P and S prime. And now this is just F of 0 plus G of 0 U of P and S. And now we know what U bar U is, and so this is equal to minus E over 2 pi cubed PA over P0 delta S S prime times, well, I started the G, but I meant to write F, but it doesn't matter since addition is abelian. Okay, now we're going to set A. In fact, I should have said A equal to 0. Well, no. We're now going to set A equal to 0 in this equation. The P's cancel. And we also had the earlier relation, P prime S prime J0 0 PS is minus E over 2 pi cubed delta S S prime. So comparing the two, what we get is a normalization condition, namely F of 0 plus G of 0 is equal to 1. So that's a normalization condition that is important in this calculation. So we switch here.
Last week you were going over this, and we did use G of 0 to calculate alpha, right? Was it?
Give me that
Last week you did part of this, and you were using G of 0 and came up with an estimate for alpha with like E squared over H bar C.
Alpha, you mean the alpha over 2 pi?
Yeah,
I don't
which
think
was
that
Right,
was-
that's the direction of the magnetic
was that
moment,
not-
yeah.
I don't think that was that G of 0.
was it not the same?
No.
We're talking about the same vertex correction. And the vertex correction, part of the vertex correction can be used to calculate the magnetic moment of the electron.
Well, the reason I was asking.
So I'm getting to that.
Oh, okay. Well, my battery's dead, so I can't look at my notes from last week. But
The notes are going to be online.
I was thinking F was divergent.
Yes.
Yeah, badly, right?
Well, yeah. But you know, there is this whole song and dance. Great question. You're right. G is finite, but F is divergent. Only logarithmically. But when we write F in this equation, and in fact everything on this blackboard, what we mean is that we've used the whole Lagrangian that has the counter terms, and we cancel things with the counter terms. Now, I have not yet done on the board, and I think I may actually just skip it, because it's a little bit of a mess. Those counter terms then you can use to make F finite. And when you, so when you do make, when you do use the counter terms, you choose them so as to get this condition. So that's the idea. All right, now we've got Dirac's equation on the board several times. Let me use it to do the following. Let's suppose we have U bar prime I
P plus P prime A plus 2m gamma A U. Okay, so what is this? We can write this way as U bar prime I P plus P prime A. So I haven't changed that. But what I'm using is that 2m or m can be written as minus P slash when acting on this, and as minus P prime slash when acting on that. Using the Dirac equation, which is up there, and which I wrote down several times. So this gives us minus I P prime slash gamma A minus I gamma A P slash. Notice that we can put the m on either side of gamma A because it's just a number. And now we can keep these two terms and rewrite this. And what we're going to do is we're going to write it as U bar prime 1/2 I, an anticommutator of gamma A with P prime slash plus 1/2 I anticommutator of gamma A with P slash, and then minus I P prime slash gamma A minus I gamma A P slash U. All right, now if we combine these together, we can see that this is actually U bar prime 1/2 I commutator of gamma A with gamma B times P prime minus P B. And maybe I'll write this like that. U. All right, so now that we have this expression, we can use this to rewrite the U bar prime gamma A, P prime and P, U, which is U bar prime gamma A F of Q squared minus I over 2m P plus P prime A G of Q squared U. What we're going to do is we're going to rewrite F a little bit. And we're going to rewrite it this way as minus I over 2m U bar prime P plus P prime A times F of Q squared plus G of Q squared minus 1/2 commutator gamma A gamma B P prime minus P B F of Q squared U. So basically what we've done here is we've rewritten this thing in such a way that the coefficient of F is the same as the coefficient of G. And then the leftover piece, we, via this identity, we expressed this way. Okay, now this gamma A, this commutator of gamma A with gamma B, if you remember from Weinberg's chapter 5, that's what the generators of the Laurens group look like in the
direct representation of the Laurens group, which is the 1/2 0 plus 0 1/2 representation of the Laurens group. So I'm going to make that explicit, and then once we do that, what we'll see is that we'll make a connection with angular momentum, which is what's related to the magnetic moment. Okay, so in particular, Ij, this is Ij being spatial. This is minus I over 4 commutated gamma I gamma j. And if you write out this commutator, this is minus I over 4. This is the commutator of minus I 0 sigma I minus sigma I 0 with minus I 0 sigma j minus sigma j 0. And now you see what happens is the two minus i's give you a minus sign. So this is I over 4. And then you just have the commutator of those, and then what you get is minus sigma I, sigma j, plus sigma j, sigma I, 0, 0, and then down here, minus sigma I, sigma j, plus sigma j, sigma I. So you get that structure. And the basic rule for the Pauli matrices is sigma I, sigma j. Well, actually, a nice rule for this is delta ij plus I epsilon ijk sigma k. I'm doing that directly from memory, so let's just see how this pops out. This is then minus I times I. So a minus I times I, epsilon ijk, and we're going to have a sigma k here, 0, 0, and we're going to have a sigma k there, and we have a 4. Oh, and we have a 2. And I actually got it right. Epsilon ijk over 2, sigma k 0, 0, sigma k. So that's what the generators of rotations look like. The generators of boosts look like this, J of I0. This is a minus I over 4 commutator of gamma I with gamma 0. And I'll just write down the answer. It's I over 2 sigma I 0, 0 minus sigma I. And this should ring a bell with what I said to you often, namely that the 2x2 representations of the Laurens group can be written as e to the z dot sigma, where z is a complex 3 vector. The imaginary part of z is the rotations, and they come out the same whether it's 1/2 in both representations of the Laurens group. The rotations look the same. However, the boosts come out with a plus sign in one and a minus sign in the other. And they correspond to the real part of Z. And so in effect, you can say that so let me see, the boosts e to the, I guess it's minus z star dot sigma, is that right? The imaginary part, I want the imaginary part to be the same, so if I do a minus a complex conjugate, that'll keep it the same. On the other hand, that'll flip the real part. So these are the two representations of the Laurens group that are referred to here as 1/2 0 and 0 1/2. And okay, so now what we're going to do is we're going to take those formulas and set P and P prime equal to 0, the vector part at least. So we're going to low momentum because after all, magnetic moment is how the electron behaves in magnetic fields when it's moving very, very slowly. And so what we're talking about here is U bar of 0 S prime, gamma A, gamma B, or rather I should have said gamma I, gamma J. So let me fix this. I, J. U of 0 and S. This is then 4I epsilon I JK, JK 1/2 S prime S, which is 2I epsilon I JK sigma K S prime S. All right, we need a K on that S. So we have a and then the other one, the boosts really don't play a role here. U of 0, S prime, gamma A, gamma 0, U of 0 and S, this is just 0. And this is not immediately obvious to me why that's so, but it is so. So we're going to go to low momentum. So low momentum, and we're going to look at this vertex. So we have U bar of P prime, S prime, and now we're writing this as a vector, gamma of P prime and S, because we're just considering spatial values of A, U of P and S, and this then is approximately, so what happens is we're going to basically ignore these terms because at low momentum, what you have is just the momentum over the mass, and then the 0, the gamma, low momentum over the mass, and in any case, it's this term that has to do with the magnetic moment. So we're going to focus on this part of it, which is 1 over m, P minus P prime, cross J 1/2 K S prime S. And what's left is F of 0. And so this is 1 over 2m P minus P prime cross sigma S prime S times F of 0. On the other hand, the interaction that we're talking about is something like this. J of x dot A of x d cubed x. And so the matrix element is P prime, S prime, H prime, PS. And this is then something like IE F of 0 over 2 pi cubed 2m integral e to the I p minus p prime dot x a of x dot p minus p prime cross sigma of s prime s d cubed x. Now you, this p minus p prime you can think of as a derivative, and you integrate by parts, and what you get is that this is e f0 over 2 pi cubed 2m integral e to the I p minus p prime dot x b of x, b being curl of a, dot sigma s prime s d cubed x. You're imagining that p and p prime are very small, and so this, or in any case, it's delta of p minus p prime times 2 pi cubed. So this gives us e f of 0 over 2m b dot sigma s prime s times delta cubed of p minus p prime. That then identifies the magnetic moment as minus e over 2m times the form factor f of 0. So that's the analytic derivation of things. So in other words, and of course this is the form factor we normalized. And so another way of writing it is to say this is e over 2m 1 minus g of 0. Do I have the signs right? Let's see. F plus g equals 1. So F is equal to 1 minus g. There's a minus sign here. But what people do is they typically ignore that. I think they typically ignore the minus sign. All right, anyway, we got Weinberg, the lowest order result when we did the calculation last week was, or Monday, I guess, was that g of 0 was minus e squared over 8 pi squared. And so we got the result that mu was, I guess, people blow away the minus sign. Anyway, e over 2m, 1 plus e squared over 8 pi squared. And this is, people write it as e over 2m, 1 plus alpha over 2 pi, where alpha is the fine structure constant. Alpha being h bar c over, no, it's e squared over, let me write it in ordinary units, it's e squared over 4 pi, and I forget where the h bar c's go, so let me not try to do anything about that. Now, what I actually did this afternoon was I looked up the latest result. Last time I told you that a Japanese physicist named Kinoshita had been doing the best calculations. He was at Cornell, and more recently he became based in both Cornell and Japan. I forget where in Japan. And the work that he's done is really quite remarkable. I guess I'll use this blackboard. The experimental value is 1.00 1159 652 18073. This is, and plus or minus 28 in the last two digits. Time is, of course, E over 2m. And this is work done by Gabrielsi. I have no idea how to pronounce the man's name, et al. He was doing work at Harvard. I think he's moved on to Northwestern, but I'm not sure. Anyway, that, at least as of 2008, that was the best value. The theoretical value by Kinoshita et al. Is 1.0011 59652 18178 times E over 2m. So you see, the error here is in these last three digits. But there's agreement to 11 decimal digits.
He's the one that was doing, you said, up to 10 loop corrections?
Right.
This
Kinoshita is up to, has done 10 loops. And that's pretty remarkable. Of course, the integrals become very complicated, and so they use, well, all sorts of techniques, but in particular, they use Fortran and do the things numerically. And they also use a Monte Carlo code called Vegas, which is a way of doing numerical integrals that are multidimensional. You just you Monte Carlo them, and in this theoretical computation, most of the uncertainty is due to hadronic effects and to uncertainty in alpha experimental, which is, of course, roughly 1 over 137, but the best measurements of it are such that the errors in the best estimates of the, in other words, when you do this calculation, obviously you get E over 2m. What's E? Well, E is essentially square root of alpha apart from 4 pi. And so the experimental value of the fine structure constant plays a role here. And the disagreement between theory and experiment is mainly due to hadronic effects and due to uncertainty in the measurement of alpha. And so Kinoshita et al. Say that the best way of testing quantum electrodynamics is to focus on something that bypasses, at least I think that's what they say, something that bypasses fine structure constant. I printed out his picture, his paper, and let me just show you some of the 8th order diagrams. One of the 8th order diagrams looks like this. So instead of, so you've got, well, let me draw it the way I've been effectively drawing things like this. It has a loop like this, and then this turns into an electron-positron loop, but then you get 2 vertex corrections here. So this is, you might call this a baseball diagram. 10 loop, one of the diagrams, well, one of the simplest diagrams is so 4 loops in the photon that goes around, that's one of them. Another one is, and this looks like a dirigible attached to the ground. They left out this part. Anyway, these are the various 10-loop diagrams. I get the impression that Kinoshita either retired or died sometime in the last 6 years. He was doing these calculations, I think, when I was a graduate student. So he's been at this for a very long time. And these are these show you the physics. By the way, when I said the theoretical calculation, I should have mentioned, I just alluded to hadronic effects. He also includes, this is a complete standard model calculation. So everything in the standard model he puts in, if it's relevant, and he adds nothing beyond the standard model, and then computes to this accuracy. Now, of course, 6 years have gone on since this paper, and so I don't know. It may be that that his group has a newer result. I guess I could search for it by using, instead of Kinoshita, I could use the names of some of the other people in the group.
Is that a PRL? Where is that?
Huh?
Where is that paper from?
Oh, I put the reference to both of these papers in the notes that are online, so you can just look at the online notes. All right, we can
Okay.
stop.